Is nature really as strange as quantum theory says, or are there simpler explanations? New neutron measurements prove that it doesn't work without the strange properties of quantum theory. Can a particle be in two different places at the same time? In quantum physics, it can. Quantum theory allows objects to be in different states simultaneously, known as a superposition state. Quantum superposition combines different observable states. But is this really the case? Perhaps the particle is actually in a very specific state, at a very specific location, but we just don't know it. The question of whether the behavior of quantum objects could be described by a simpler, more classical theory has been discussed for decades. In 1985, a way of measuring this was proposed, the so-called Leggett-Garg inequality. Any theory that describes our world without the strange superposition states of quantum theory must obey the Leggett-Garg inequality. Quantum theory, on the other hand, violates it. Measurements with neutrons testing this inequality have now been carried out for the first time at TU Wien, with a clear result. The Leggett-Garg inequality is violated. Classical explanations are not possible. Quantum theory wins. The results have been published in the journal Physical Review Letters. We normally assume that every object has certain properties, like a ball being at a certain location with a certain speed. This view is known as realism, says Stephan Sponar from the Atomic Institute at TU Wien. Macroscopic objects in particular must obey this rule. However, quantum theory as we know it today violates this macroscopic realism. If different states are possible for a quantum particle, then any combination of these states is also possible, at least until measured. Testing macroscopic realism experimentally is not easy. We need an object that is macroscopic in a certain sense but still shows quantum properties. Neutron beams, used in a neutron interferometer, are perfect for this. In the neutron interferometer, a silicon perfect crystal interferometer splits the incident neutron beam into two partial beams and then recombines them. Quantum theory says that every single neutron travels on both paths at the same time, says Niels Geerits. The two partial beams are several centimeters apart, making it a quantum object that is huge by quantum standards. Using a sophisticated combination of several neutron measurements, the team at TU Wien tested the Leggett-Garg inequality. The result was clear. The inequality is violated. The neutrons behave in a way that cannot be explained by any conceivable macroscopically realistic theory. They actually travel on two paths at the same time, located at different places, centimeters apart. The idea that maybe the neutron is only traveling on one of the two paths, we just don't know which one, has been refuted. Our experiment shows nature really is as strange as quantum theory claims, says Stephan Sponar. No classical, macroscopically realistic theory can explain reality. It doesn't work without quantum physics.